Okay, this is a pre-calculus review talking about proper rational expressions and divisions of polynomials. This will help with techniques of integration by partial fractions. All right, so what is a rational expression? A rational expression is one that is a quotient of a polynomial over and another polynomial. So this would be a p of x over a q of x, where p of x and q of x are polynomials. Okay, so some examples would be x squared minus 1 over x cubed plus 2x plus 1, something like that. So those would be the ratio or the quotient of a polynomial and another polynomial is a rational expression or a rational function. And when we do techniques of integration using partial fractions, we will be looking at the integrals of rational functions where a standard U substitution may be difficult. Okay, so backing up with polynomials, the degree of a polynomial is equal to the value of the highest exponent among the terms of the polynomial. So the degree of a polynomial is equal to the value of the highest exponent among the terms on x. So in the case above, the degree of the numerator, the degree of x squared minus 1 is going to equal 2, and the degree of x cubed plus 2x plus 1. The degree of a constant is 0, by the way, but x cubed has 3 as its degree, 2x has 1 as its degree because the value of the exponent on 2x is 1. But the degree overall is the highest exponent, and that highest is 3. Good? So that is helpful in determining whether or not a rational expression is proper or improper. So what is a proper fraction? A proper fraction is one where the numerator is strictly less than the denominator. And so some examples, 1 over 2 is a proper fraction. In other words, the ratio is strictly less than 1. Good, so where a over b is strictly less than 1, so that tells me the numerator is strictly less than the denominator. And an improper fraction is the exact opposite. It is where the numerator is greater than or equal to the denominator. So some improper fractions would be 3 over 3 or 3 halves, etc., etc. Doesn't matter if they're positive or negative, they would still be improper. Good. So in this case, the improper fraction would be that a over b would be bigger than 1, or a over b would be less than negative 1. So it would be like negative 2.5 or negative 5 halves would be an improper fraction. All right, so you can apply that same type of idea to the what is a proper rational function or rational expression is one where p of x over q of x is where the degree of the numerator is strictly less than the degree of the denominator. And an improper rational expression is one where the degree of the numerator is bigger than or equal to the degree of the denominator. Right? Or degree of p of x is less than the degree of the q of x in the case of proper rational expressions, and here the degree of p of x would be bigger than or equal to the degree of q of x if it is improper. Now the very first step in applying the technique of integration by partial fractions involves securing the rational expression that you have is proper. And if it is not proper, in other words, if it's improper, then we want to convert that rational expression into, we want to divide the denominator into the numerator and express it as its quotient plus its remainder, and then perform techniques of integration on the remainder. So that might involve division of polynomials if you're going to be successful in calculating an integral using partial fraction decomposition. Okay, so I'm going to skip ahead and go, this is just a brief review of division of polynomials. And I usually go by way of reminding people, how do we divide fractions? Or how do we divide numbers? So if I had a over b, that's going to equal a divided by b, and that's going to be b going into a. So if I had something like 129 or 128 divided by 3, this is going to be 3 goes into 128. And I would go through the motions of 3 times what gives me 1. That's not enough. So I would take 3 times what gives me 12, and I would say 4. And what do I put on the outside? I would put the top times the outside. And that would be 4 times 3, so I would put 12 here, and then the next step would be I would subtract. And in my subtraction, 12 minus 12 is 0, and then I would drop down the 8, and I would begin again. And I would say 3 times what gives me 8 without going over. 3 times 2 does, and what do I put here? I put the top times the outside. And the top I put 2, and the outside is 3, so I would be putting here 6, and then I would be subtracting. 8 minus 6 is 2, and when I have nothing left to drop down, my 2 and 3 does not go into 2. This is my remainder, and what do I do with my remainder? I say that then this remainder is 2 over the outside. Right? So we can see that 128 over 3 is going to give me 42 2/3. Good? So the same idea applies to polynomials, only we include our equal sign, or our positive and negative, or addition and subtraction in between, and we also ensure that we are lining up our like terms. So just as an example where we have all of our terms in descending order, let's say we have x, or 3x to the 5th minus 2x to the 4th plus 7x cubed plus 2x. I'll just skip the 1 there, and then minus 1 divided by, let's say, x squared plus 4. Good. This, I can see that is improper because the degree of the top is 5, and that is bigger than the degree of the bottom, the denominator, and the degree of the denominator is 2. So we have an improper rational expression. So the first thing that we would want to do is divide the denominator into the numerator. So I tend to, when I don't have all descending powers of the numerator and it's underneath my division sign, I tend to put a placeholder so that I can ensure that I can collect like terms. So I have 3x to the 5th minus 2x to the fourth plus 7x cubed plus 0x squared, because we don't have any x squares. So I'm actually going to put a placeholder in there just in case we need it. And then I have plus 2x minus 1. All right. So I'm going to start with my very first term here, x squared, and I'm going to be looking at my very first term underneath the quotient, and I'm going to say x squared times what gives me 3x to the fifth. So I have a 1 here, 1 times 3, and then I need 3 more x's. Good. So I have 3x to the third times x squared is going to give me 3x to the fifth. So what do I put here? I put the top times the outside. And what's the top? The top is 3x cubed. The outside is x squared to plus 4. And I'm going to distribute that. And I'm going to say that this is 3x to the fifth. And then 3x cubed plus 4 is 12x cubed. So I'm going to actually put that underneath the 12x cubed because I want to line up my like terms. And then what do? We subtract, right? But we're subtracting the entire 3x to the fifth plus 12x cubed. And if I were to subtract horizontally, I would first clear my parentheses by distributing the minus sign. And distributing a minus sign would change the sign on the inside for each of the terms. So if I'm going to distribute that minus inside, that's going to turn this one into a minus, and it's going to turn the 12 into a minus. And now I'm going to be able to collect my like terms, and we know that we've gotten the right quotient if the very first term goes away. That's going to give me 0. And here we have 7x cubed plus negative 12x cubed is going to be minus 5x cubed. And then I drop one down and I begin again. So in this case, since I skipped over, I'm going to be dropping down the minus 2x to the fourth. And now I'm going to begin again. And I say x squared times what gives me negative 2x to the fourth. I know 1 times what gives me minus 2 is going to give me a minus 2. And x squared times x squared is going to give me x to the fourth. So what do I put here? I put the top times the outside, and the top is minus 2x squared. The outside is x squared plus 4, and if I distribute, I end up with minus 2x to the fourth, and then I have minus 2x squared plus times plus 4 is minus 8 x squared, right? And since I don't, and I want to line it up with my like terms, right? So when I go to subtract, I'm subtracting the correct terms. Again, what's my next step? I want to subtract, and to subtract the entire polynomial, I clear my parentheses by distributing the minus, and so this minus turns the negative 2 into a plus, and it turns the minus 8x squared into a plus, and now I can collect my like terms. Negative 2x to the fourth plus 2x to the fourth is 0. I can drop down my minus 5x cubed, and 0 plus 8x squared is plus 8x squared. And now I can begin again. What x squared times what gives me minus 5x cubed? I get minus 5, and then I need one more x. So I put here top times the outside, and what's on top? Minus 5x. What's on the outside? X squared plus 4. If I distribute, I end up with minus 5x cubed, and this ends up being minus 20x, and I want to put that next to here, and I want to drop down my plus 2x. Good? And so my next step, again, just like with long division, is to subtract. And in order to subtract, I want to clear my parentheses, distribute again, and this is going to turn this one into a plus. It's going to turn this one into a plus, and now I'm going to be able to collect my like terms, and I end up with this one going away. I can drop down my 8x squared, and 2x plus 20x is plus 22x, and I can drop down my minus 1 as well. And now finally I'm going to have one last step to make. X squared times what gives me 8x squared? I get plus 8. And I'm going to put top times the outside. And what did I put on top? 8. What's on the outside? X squared plus 4. So I distribute my 8 and I end up with 8x squared plus 32. And what do? I subtract. And in subtracting, I'm subtracting the entire expression. I want to distribute the minus, and that turns the 8 into minus 8, and it turns the plus 32 into minus 32. Good. 8x squared, negative 8x squared goes away. There's 22x, and minus 1 and minus 32 combine to be minus 33. And now this is my remainder because it is smaller than x squared plus 4. Good? So what do I do with my remainder? I say this is plus, and I do 22x minus 33, and it's all over the outside. So my quotient is now equal to 3x cubed minus 2x squared minus 5x plus 8 plus a remainder of 22x minus 33 all over x squared plus 4. And that's how I transform my rational expression in preparation for integration using partial fractions. If I did have to integrate this with respect to x, I could use my algebra of functions and say that this is an integral of 3x cubed minus 2x squared minus 5x plus 8 dx plus the integral of 22x minus 33 over x squared plus 4 dx. And actually for this one, I would not be using partial fraction decomposition because I would be using a combination of u substitution and the inverse tangent, but that will come clear when we do partial fraction decomposition. But now this would apply because now this is a proper rational expression. More to come on partial fraction decomposition method for integration. So hopefully that was helpful in preparing you for that section, and there you have it.